Today's speaker is a Rutgers Experimental Mathematics Seminar. Is a good old alumni, Eric Sundberg, who got his PhD approximately 10 years ago.
I think it's more than that. It was
okay, more than roughly 10 years ago, under the guidance of Professor Beck, who will talk about some neat tic-tac-toe games. Thank you.
Thank you. All right, thank you, Doran. Okay, so I'm going to start off by defining positional games. That's the name we use for these tic-tac-toe style games. Then I'll define the specific game that we're going to be looking at, which will be tic-tac-toe on the n-dimensional Boolean hypercube with k-dimensional subcubes as the winning sets. Then I'll talk about pairing strategies for that game, and then how we can build pairing strategies for higher dimensional games based off of pairing strategies for the lower dimensional games. I'll mention a couple of earlier theorems, then I'll mention our main theorem and a couple of stronger theorems. Then after that, we'll talk about the ideas behind the proof of the main theorem, and we'll do that through an illustrative example. All right, so positional games are like generalizations of tic-tac-toe, except they can be played on an arbitrary hypergraph like this one here in the middle. And what's going on is there are two players and they're taking turns occupying previously unoccupied vertices, and they're both racing to be the first player to occupy all of the vertices of one of the edges in the hypergraph. And we can think of traditional 3x3 tic-tac-toe as a positional game on a 3 uniform hypergraph in the following way. The 9 positions, those would be the vertices of the hypergraph. And then the 8 winning lines, the 3 verticals and the 3 horizontals, and then the 2 diagonals, those would be the edges in the hypergraph. And then over here on the right, I've drawn a picture of a 3-dimensional Boolean hypercube, and I've highlighted one of the 2-dimensional subcubes because those will be the winning sets in one of the examples that we look at. All right, so what I want to do now is real quickly just step away from the slides for a little bit and do a little review of the Boolean hypercube. So we can think of this right here like a single vertex. We could think of that as a 0-dimensional Boolean hypercube. And then if we take 2 of those and connect them with an edge, then we get a 1-dimensional Boolean hypercube. And when you do that, you could label the vertices with length 1 bit strings. So that could be 0 and that could be 1. And then you can take a couple of those 1-dimensional Boolean hypercubes. We would call each of these Q1, take 2 of those, connect the corresponding vertices, you'll get a 2-dimensional Boolean hypercube. And we would call this Q2. Again, we can label the vertices, in this case with length 2 bit strings. And this could be 0, 0, this could be 1, 0, this could be 0, 1, and that could be 1, 1. And what we're doing here is we're connecting 2 bit strings or 2 vertices with an edge if and only if they differ in exactly 1 coordinate or they differ in exactly 1 bit. And then we can keep going like this. We can take 2 of these, connect the corresponding vertices, we get a 3-dimensional Boolean hypercube. Here we would label the vertices with length 3 bit strings or length 301 vectors. We could take 2 of these, do like a little small one and then a bigger one on the outside, connect the corresponding vertices, and we'll get the 4-dimensional Boolean hypercube. And we would label these with length 4 bit strings. So what we want to do is play a little tic-tac-toe game on one of these.
And you keep doing it indefinitely? Have a nice model.
Yeah, you can just keep going like that. Just keep doubling it and connecting the corresponding vertices. And they end up making the subset lattice because the bit strings can be associated with the subsets of like a set of cardinality n. And so if we could play a tic-tac-toe game on one of these in the following way, we can have the 2 players take turns occupying unoccupied vertices. I'm going to put a little purple flag if the first player occupies a vertex, little green flag if the second player occupies a vertex. And then I should say, well, what are the winning sets? How about we start off with the winning sets for this game will be these 1-dimensional subcubes. And you see we have 4 of them up here on the top, 4 of them down here on the bottom, then that perfect matching of 4 connecting the top and the bottom. So we have 12 winning sets here. And very obviously the first player has a winning strategy because once the first player moves, no matter where the second player moves, there'll always be at least 2 neighbors of that first player's move that are unoccupied and then the first player can occupy one of those neighbors and occupy a one-dimensional subcube. So we would say that the first player has a winning strategy for, I'll call it the Q3-1 game, because we're playing on the three-dimensional Boolean hypercube with one-dimensional subcubes as winning sets. Then we could change the winning sets to the two-dimensional subcubes and play a different game, the Q3-2 game. And we have the 6 winning sets, which correspond to the 6 sides of the cube. And if you think about this for a little bit, you'll see, well, the second player would very easily be able to force a draw in this game. And what I want to talk about is a specific strategy that the second player could use to force a draw called a pairing strategy. So if you notice, I've put flags, little flags on 3 of the edges here, and that corresponds to the second player's pairing strategy. And the way it works is if the first player ever occupies one of the vertices that's an endpoint of a flag with an edge on it, of an edge with a flag on it, the second player immediately responds with the other endpoint, and vice versa. If the first player were to occupy this endpoint, the second player would immediately respond with the other endpoint. And once we know that the second player is doing that, then all we have to do is make the following observation. First, notice that if any one of these two-dimensional subcubes or one of these winning sets contains an edge with a flag, the first player will never be able to occupy all 4 vertices of that subcube. And that's because we know the second player is going to occupy at least one of the 2 endpoints of each edge that has a flag. And then all we have to do is check, well, does every one of the 6 two-dimensional subcubes have an edge with a flag? And then that's not too hard to do. We notice that each one of these edges with a flag ends up blocking 2 subcubes, and the subcubes that they are blocking are distinct from each other. And so with the 3 flagged edges, we block all 6 of the two-dimensional subcubes. So we know that the second player can force a draw in the Q3-2 game. And so we've actually solved the 3-dimensional game. We know that for subcubes of dimension 1 or smaller, the first player will have a winning strategy. But for subcubes of dimension 2 and higher, then the second player can force a draw. We could ask a similar question for the game on the 4-dimensional Boolean hypercube. Again, we'll say very easily the first player has a winning strategy when the winning sets are of dimension 1 or smaller. But then we'd ask, well, what happens if the winning sets are of dimension 2? Who would have a winning strategy? Would the first player have a winning strategy, or could the second player force a draw? And maybe the little flags are a hint as to what happens. And indeed, these flags represent a pairing strategy that allows the second player to block all of the 2-dimensional subcubes in this Q4 here. So we've also solved the 4-dimensional game. For subcubes of dimension 1 and smaller, the first player has a winning strategy. And for subcubes of dimension 2 and higher, the second player can force a draw. And in general, what we're looking to do is we're looking to find, given n-dimensional Boolean hypercube, what is that dimension k? What's that value of k? So that for subcubes of dimension k and lower, the first player will be able to occupy a k-dimensional subcube. And then for dimension k plus 1 and higher, the second player can force a draw. That's the general question that we're asking. And for general and
the second player can never win.
Yeah, so there's this strategy stealing argument for these tic-tac-toe style games that's saying if you have the extra move, it never hurts you. So yeah, the second player can never win. The best the second player can do is force a draw. And frequently what we do is we change the rules to the maker breaker version, and the first player will be called maker, and she's only trying to occupy a winning set, and the second player would be called breaker, and he's only trying to prevent maker from occupying a winning set. And if breaker prevents maker from occupying a winning set, then breaker wins. If breaker occupies a winning set, that doesn't necessarily mean anything. And so that's the way like the paper is written. It's written in the maker breaker form. And actually, I'm probably, when I state what we're looking for, like looking for that value of k where I should say the value of k where maker would have a winning strategy, and then for k plus 1 and higher, breaker has a winning strategy, because we don't have any good strategies for the first player under the normal rules. Those are very hard games to study. So we almost always switch to the maker breaker scenario. All right, so let me go back to the slides here. And these next few slides are just pretty much a review of what we just talked about with the little models. Here's a picture of a three-dimensional Boolean hypercube. We can label the vertices with these length 3, 0, 0, 1 vectors. Let me just put the all zeros vector here. The X is to signify that we change the first coordinate when we go in this direction. So this would be 1, 0, 0. The Y, we change the second coordinate, that would be 0, 1, 0. The Z, we change the third coordinate, that would be 0, 0, 1. Right here is one of our two-dimensional subcubes, or one of our winning sets for the Q3-2 game. And notice that these two-dimensional subcubes, this one right here, it's precisely the set of 4 vertices whose second coordinate is 0. I put the little stars here. This is sort of shorthand for that two-dimensional subcube. These little stars just represent that the first and the third coordinate can be whatever they want, and you end up getting the 2 times 2, the 4 different vertices of that subcube. And we're going to be using this notation in the idea of the proof. Just a review: if 2 vertices are paired together in second player's pairing strategy, then if the first player occupies one of the vertices, the second player immediately responds with the other, and vice versa. If the first player takes this vertex, second player immediately responds with that one. In the pairing strategies that we use, we're going to have the second player always pair together 2 endpoints of an edge. That's sort of a greedy approach. And I'll make the observation: notice that an edge corresponds to a one-dimensional subcube, right? 1 star would be a one-dimensional subcube. So one-dimensional subcubes and edges are the same thing. And when an edge is inside of the second player's pairing strategy, instead of using the star right here, I'm going to use a V. And that's so that we can quickly spot, well, which edges are part of the pairing strategy and which are just one-dimensional subcubes that we sort of have to take care of. Sort of summarizing this together, in general, our pairing strategies for the Q and K game will always correspond to matchings, because the second player will always pair together 2 endpoints of an edge. And then they have to be matchings because suppose these 2 vertices are paired together and these 2 vertices are paired together. If they actually share a vertex and the first player goes in that shared vertex, I know I'm covering it up with my finger here, but if the first player goes in that shared vertex right there, then the second player doesn't know, do I respond with this one or that one? But if it's a matching, then it's very clear. And in general, the way that pairing strategies are described is they're described as a disjoint set of pairs of vertices. The pairs have to be disjoint from each other. So we need a matching for our pairing strategy. The other property that we're going to need is that every one of the k-dimensional subcubes, in this case, the 2-dimensional subcubes, are going to have an edge from the pairing strategy in them to guarantee that the second player blocks all of the k-dimensional subcubes. And then this is the picture of our pairing strategy for the 3-2 game. And you can check if you want. All of these 2-dimensional subcubes, the little squares, contain one of these salmon-colored edges. So here's a lemma that Klay, Kruczek, and I proved. We proved that if there's a drawing pairing strategy for the Q and K game, then there's also a drawing pairing strategy for the Q n+1, K+1 game. So the dimension of the board increases by 1, but also the dimension of the winning sets increase by 1. And since we have this pairing strategy for the Q3-2 game, if we repeatedly apply our lemma, then we get a pairing strategy for the Q4-3 game, the Q5-4 game, the Q6-5 game, and so on. In general, we get a pairing strategy for the Q and n-1 game for each n greater than or equal to our starting value of 3. And since we found a pairing strategy for the Q4-2 game, we repeatedly apply our lemma, and there's a little gap of 2 here. So we get that there's a pairing strategy for the Q n-2 game for each n greater than or equal to this value of 4. And then using Mathematica, we were able to find a pairing strategy for the Q7-4 game. And then because of this gap of 3, that gave us a pairing strategy for the Q n-3 game using our lemma. And that was starting at n = 7. We worked a little harder with Mathematica. We were able to slightly improve that. We found a pairing strategy for the Q6-3 game. And all that didn't change this result over here because it's still a gap of 3, but we did get the starting value down by 1, down to starting at 6. And then using like similar approaches to finding our pairing strategy for the Q6-3 game, we found a pairing strategy for the Q8-4 game, which gave us the n-4 result. And then lastly, for the Q10-5 game, and because of that gap of 5, we got the pairing strategy for the Qn-5 game for each n greater than or equal to 10. And if you sort of look at maybe the last 3 results, we have the 6-3, 8-4, and 10-5. That led us, of course, to conjecture, well, maybe we can find a pairing strategy for the Qn-n/2 game. We won't be able to use this lemma to find such a pairing strategy, but maybe some other approach will work. And Ramin, Naimi, and I were able to come up with this theorem right here that says if there's a drawing pairing strategy for the Qn-k game, then there's a drawing pairing strategy for the Q4n, B game, where B is the larger of 4k minus 3 and n plus k. And a nice corollary to that result is, I'll focus on bullet point 2 down here, is if you have a drawing pairing strategy for the Qn-k game, and the dimension of the winning set k has this nice form of it's 1/3 the dimension of the board, and you can go ahead and put the floor function on that if you want, and then +1, then there will also be a drawing pairing strategy for the Q4n. So we increase the dimension of the board by a factor of 4. Again, we keep the same nice form, 1/3 the dimension of the board. You can put the floor function on there if you want, and then +1. And the second player is able to block subcubes of that dimension right there. And since our drawing pairing strategy for the Q3-2 game actually has that nice form, this one right here is 1/3 the dimension of the board. Here's the little +1 that we had. Since the Q3-2 game has that nice form for the dimension of the winning sets, then we can repeatedly apply bullet point 2, and we get that for games on boards whose dimension is 3 times the power of 4, the second player is actually able to block subcubes whose dimension is essentially 1/3 the dimension of the board. Our first stronger theorem has a very similar result. It says if the dimension of the board is a power of 3, then the second player can block subcubes whose dimension is again basically 1/3 the dimension of the board. But this stronger theorem has a nicer little addition to it. We have that there are actually 4 to the d+1 disjoint pairing strategies for that game. And together, the edges in those pairing strategies partition the set of edges of the board that you're playing on. And then here's the picture in the case d equals 0. It's the 3-2 game, and there are 4 pairing strategies. The color classes are the 4 different pairing strategies. And you see the edges are partitioned by these color classes. But the other neat little thing is if you look at each of the winning sets and think about what's going on, each of these pairing strategies will have an edge in each of the winning sets. So these pairing strategies together, they rainbow color the winning sets for the game. So each winning set gets an edge of each color. Now, our strongest result was for games whose board is a power of 4. And in this case, the second player is able to block subcubes of dimension, basically 1/4 the dimension of the board. Again, we get the 4 to the d+1 disjoint pairing strategies that partition all the edges of the board. And again, we get that rainbow coloring property on all of the winning sets. So those are the results that we have. And I guess I could ask, does anybody have any questions at this point?
Yeah, are there a sharp or it's possible that you can improve them?
I suspect that we could probably improve these quite a bit. And there are also like 2 questions floating around, like the idea of finding like the value of k, where that's the highest dimension winning set that maker can occupy, and then k+1 and higher than the second player or breaker could win. Usually the pairing strategies don't do a good job of finding that value of k+1. There are many other types of strategies that do better than pairing strategies. I just like the pairing strategies because I think they're like really, really beautiful and fun to work with. So there are these potential-based strategies like the Erdős-Selfridge theorem that typically do much better than pairing strategies. And there are a few like low dimensional games, like the ones I talked about, like with these pictures where the pairing strategy is sharp, but other than that, I don't think it's going to be sharp in general. But there's also the question of finding what's the best that you can do with a pairing strategy. And I haven't had much success yet with that, with like proving a general theorem of like, this is, you know, like the best you can do with a pairing strategy. And theoretically, there's a general theorem about pairing strategies that for this game would say, theoretically, the best you could do would be natural log of n. And we're not really getting close to that theoretical bound with our n/4 in the special case. Yeah, thanks. All right, so I guess I'll move on to some of the ideas in the proof here. And in order to look at the proof, I want to focus again on this sort of vector notation for our subcubes and our edges over here. And we're going to want to know, like, when is one of second player's edges from his pairing strategy inside of a subcube. So I want to be able to spot that in the vector notation. And if we have a picture, it's really easy to see if a subcube contains an edge. But, you know, once I get beyond dimension 3, I don't want to look at the pictures anymore. I can't even imagine them very well myself. And this two-dimensional subcube right here, we can represent it with this vector with the 0 and star star. It's precisely the 4 vertices that have a 0 in their first coordinates. And then their second and third coordinates could be whatever they want. And we'd ask, well, do they contain this edge, this sort of aqua colored edge that can be written as 0 star 1? Well, this is precisely the 2 vertices that have a 0 in their first coordinate, a 1 in their third. Well, both of those vertices have a 0 in their first coordinate. So of course they'll be amongst the 4 vertices that have a 0 in their first coordinate. So this two-dimensional subcube would contain this edge. And I like to summarize that idea with this statement over here. All you have to check is you just have to check, does your edge match your subcube and all of the coordinates fixed by your subcube? Well, this subcube only fixes the first coordinate. It fixes the first coordinate at 0. My edge has a 0 in the first coordinate, so my edge is inside of that subcube. Let's take a look at this red edge here. Using our condition, this first coordinate is not fixed at 0, so this subcube 0 star star does not contain this edge. Well, the 2 vertices in this edge are 0, 0, 0 when we put the star equal to a 0, that's this vertex, or 1, 0, 0 when we put the star equal to a 1, and then this is the vertex 1, 0, 0 that's not in the subcube. And then if we take this edge up here, well, it has a 1 in its first coordinate. It doesn't match this 0 in the first coordinate, so neither of the 2 vertices in this edge would be in the subcube, so the subcube doesn't contain this edge over here. And then when we go to higher dimensions, which will be our goal, it works just as easily. We could ask, so this is a 3-dimensional subcube of Q6. There's 6 coordinates, so it's in Q6. 3 of those coordinates are stars, so it's a 3-dimensional subcube. The other 3 coordinates are fixed. We ask, does it contain this edge over here? This is an edge because exactly one of its coordinates is a star. And all we have to check is in the first coordinate, the 4th, and the 5th coordinate, does my edge have a 0, 1, and 0 in those coordinates? It does. So therefore, the subcube contains that edge. This new edge right here has a star in its 4th coordinate instead of a 1, so it doesn't contain that edge. And then this edge right here has a 0 in its 4th coordinate instead of this 1. So this subcube does not contain this edge over here. And that's all we have to do is check, do the edges match the subcube in all of the coordinates fixed by the subcube. The other thing we needed is we needed our edges in our pairing strategy to be a matching. So I need to be able to tell using the vector notation when 2 edges are disjoint from each other. This blue edge right here is the 0, V1. This red edge is the V0, 0. And the way I like to summarize whether or not 2 edges are disjoint, will be if I can find a coordinate where one of those edges has a 0 in that coordinate, the other edge has a 1 in that coordinate, then the two edges will be disjoint. And here the third coordinate works, right? V0, 0 has a 0 in its third coordinate, 0, V1 has a 1 in its third coordinate, so those two edges are disjoint. Let me add a new edge to the mix, this one right here. I'm going to compare it to V0, 0. And so I wrote them on top of each other because then I just check coordinate by coordinate. Check the first coordinate, well, there's a V, second coordinate, there's a V there. Then they're both 0 in the third coordinate. So these two edges are not disjoint. And then we can easily find the vertex of intersection. Just set this V equal to this 1, set this other V equal to that 0. We get the vertex of intersection 1, 0, 0. That's this vertex. And you see 1, 0, 0 would be in that edge. 1, 0, 0 would also be in that edge because the V is like a wild card. In one case, for one endpoint, it's 0. For the other endpoint, it's 1. And then again, it works the same in higher dimensions. Here are a couple of edges in Q6. And here in the fifth coordinate, this first edge has a 0. And in the fifth coordinate, the second edge has a 1. So those two edges are disjoint. Now I'll compare this edge to a new edge, which I'll write underneath it. And I just check coordinate by coordinate. They're both 0, then they're both 1. Then this is a V, then they're both 1. Then this is a V, then they're both 0. I never found a coordinate where one of them had a 0 and the other had a 1. So those two edges are not disjoint. This edge right here is just that edge up there. So those two edges are not disjoint. Okay, so here's Q42. And here I've drawn a picture of the four-dimensional Boolean hypercube, and the red edges are the pairing strategy to block the two-dimensional subcube. And we'll have to check those two properties. Do the red edges form a matching? And for every two-dimensional subcube, does every two-dimensional subcube contain one of the red edges? But I'm going to do it in the context of the vector notation. I've written the 8 edges in this vector notation. And the first thing I'll check is, do they form a matching? So for each of the, well, we have 8 choose 2 pairs of edges. And for each of those pairs of edges, I need to check, can I find a coordinate for one of them has a 0, the other has a 1. And there would be 28 pairs to check. We won't go through all of those. But if you were to do it, you'd notice that because these edges come in these sort of complement pairs, notice I changed these 3 zeros to 1s, I get the edge below it. And in the next one, I change those zeros to 1s, that 1 to a 0, I get the edge below it. They're in these 4 complement pairs. That helps this process go a lot faster because say I was trying to compare this edge to the other 7, well, of course, I can easily find a coordinate where my edge has a 0 and its complement has a 1. And if I compare my edge to the edge next to it, well, in the 4th coordinate, my edge has a 0, but the edge next to it has a 1. But because they're coming in these complement pairs, then I immediately have that their complements have a similar property. Well, this edge is going to be disjoint from that edge because in the 4th coordinate, this one had a 1 and that one had a 0. And then once I establish that this edge is disjoint from that one, because I look at the 2nd coordinate, my edge has a 0, this one has a 1, then I immediately get, well, their complements have a similar property. This edge has a 0 in the 2nd coordinate, that edge has a 1, and then you can go through the 28 pairs fairly quickly that way. The second thing that we have to check is we have to check that every one of the two-dimensional subcubes contains one of these 8 edges. And let's recall that a two-dimensional subcube inside of Q4, it's going to be a length 4 vector. 2 of the coordinates are going to be stars because it's a two-dimensional subcube. The other 2 coordinates are going to be fixed. Here's one of the two-dimensional subcubes. It fixed the last 2 coordinates at 0. And a reminder, our goal for whether or not a subcube contains an edge is you check, does the edge match the subcube in the coordinates fixed by the subcube? Well, this particular subcube has 0 in its last 2 coordinates. This edge has 0s in its last 2 coordinates. So this subcube contains this top edge here. And then we'll kind of exploit the complements again. We'll do a new subcube by changing the 0s to 1. Now the bottom edge matches that subcube in the last 2 coordinates. And then we'll just go ahead and go through all the subcubes for this case, and if we have zeros in the
Sorry,
first.
Eric, I'm confused about notation.
Oh,
what
yes.
does V mean as opposed to star?
Oh, yeah. Okay. Yeah. So the V is sort of a silly thing I did. It should be a star, but I decided when I have an edge in my pairing strategy, I'm going to use a V so that we remember, oh, that's one of the edges from the pairing strategy. But to tell you the truth, where the V came from initially was I was testing this stuff out on Mathematica, and the star was the symbol for multiplication, and that wasn't going to work well in my vector. So I'm like, I need something else, so I use a V, and it just sort of stuck. So, so that's why there's a V there. That's the real reason there's a V there. But I like to tell you that it's so that we can spot that it's part of the pairing strategy. Yeah. Okay. So the V is the coordinate that changes in the edge in the pairing strategy. And so we check the first and the second and the fourth coordinates here on this edge. They match up with this two-dimensional subcube. So that subcube contains this edge. We'll change these zeros to 1, and then the bottom edge will match up with that. We'll do the 2 zeros in the middle. The top edge matches up with that. Change them to 1s. Now the bottom edge matches. Go over here, zeros on the first and fourth. The top edge matches, change them to 1s. Now the bottom edge matches, zeros in the first and third. Now the top edge matches, change them to 1s. Now the bottom edge matches, zeros in the first two coordinates. The top edge matches, 1s. Now the bottom edge matches. Now we get to the last 12 two-dimensional subcubes where the fixed coordinates have a 0 and a 1. Now it's the bottom edge that matches. Switch it to 1, 0. Now the top edge matches, 0, 1s in those positions. Top edge matches, switch it to 1, 0. Now the bottom edge, 0, 1 in the middle. The bottom edge matches, switch it to 1, 0. Now the top edge matches, 0, 1 in the extremes. The top edge works, switch it to 1, 0. Now the bottom edge works, 0, 1 in 1 and 3. The top edge matches, now 1, 0. Bottom edge matches, and then this is the last one, 0, 1, the top edge matches, switch it to 1, 0, now the bottom edge matches. Okay, so I'm sorry for going through all 24, that was probably a little excessive, but hopefully it drives home the point to when we get to the higher dimensional versions, you're just immediately thinking, match up on those fixed coordinates and the edge will block the subcube. So I asked this question, is there some way to maybe sort of multiply our pairing strategy for the 3-2 game with our pairing strategy for the 4-2 game to get a pairing strategy for the game on the 12-dimensional Boolean hypercube blocking subcubes of some dimension k? And indeed there is. It looks like this. What we end up doing is we end up creating 8 of these Cartesian product sets. And the form of these Cartesian product sets comes directly from the 8 edges of PS42 of our pairing strategy for the 4-2 game. Notice we had this edge V0, 0. Then we make this Cartesian set V cross 0, cross 0, cross 0, and so on. Here's the edge V1, 1. And here's the Cartesian product set V cross 1, cross 1, cross 1. But of course, well, what are the little sets that we're using to create these Cartesian products? Well, the bold 0 will be the set of even parity 0, 1 vectors of length 3. The bold 1 will be the set of odd parity 0, 1 vectors of length 3. And then these bold V's will be the 3 edges from our pairing strategy PS32. Here are exactly what those sets are, right? The bold 0 has these length 3, 0, 1 vectors where each of them has an even number of 1s. The bold 1 is these length 3, 0, 1 vectors where each of them has an odd number of 1s. And then these are the 3 edges from PS32. And we create these Cartesian product sets based off of these 3 sets. And let's take a look at one of these Cartesian product sets so that, oops, well, that's terrible. So that, let me grab that. Let's take a look at these Cartesian product sets so that everyone gets a good feel for what they look like. So we are going to look at this this 0 cross 1 cross 0 cross V. And it's going to create these length 12 vectors, which will be edges inside of Q12. And we end up breaking those 12 coordinates into 4 bins here. And for the first bin of 3 coordinates, we'll have 4 choices, any one of the 4 even parity vectors of length 3. For the second bin of 3 coordinates, we'll have 4 choices, any one of the 4 odd parity vectors of length 3. And then for the third bin, 4 choices, any one of the even parity vectors of length 3. And then for the last bin, we'll have only 3 choices, any one of the 3 edges from our pairing strategy, PS32. And let's take a look at 3 example edges that would be in this Cartesian product set. We could use our first choice here, second choice here, fourth choice here, second choice there. That was just kind of arbitrary. And we get this edge down here. It's a length 12 vector with exactly 1 V. So that's an edge inside of Q12. And that edge is inside of this Cartesian product set. I could have used my third choice here, first choice there, second choice there, first choice there. Again, that's arbitrary, but then that gives us this edge inside of Q12. Maybe I'll use my fourth choice in the first bin, third choice in the second bin, second choice in the third bin, third choice in the fourth bin, and then I get this edge in Q12. And of course, there are 192 different edges in this set. The pairing strategy is the union of those 8 different Cartesian product sets that correspond to the 8 edges of PS42. So we have close to 8 times 200 or close to 1600 edges in this pairing strategy. But we want to get an idea for, well, why does this pairing strategy end up blocking all of the 5-dimensional subcubes from Q12? So let's take a look at a little example. Here's an example of a 5-dimensional subcube in Q12. It's a length 12 vector. It has 5 stars, the 3 there, the 2 there. The other 7 coordinates are fixed at 0s and 1s. And what we need to do is we need to find an edge inside of PS12.5, inside the union of those Cartesian product sets, that matches this 5-dimensional subcube on the 7 coordinates that are fixed by this subcube. So the first thing I'm going to do is I'm going to partition the 12 coordinates into these 4 bins of size 3, because that's what my Cartesian product sets look like. And then I'm going to look at this first bin right here. I see 0, 1, 1. I need to match that bin exactly. So for my first bin, in the edge that I select or that I find, I need to have 0, 1, 1 in that edge. Then I notice over here in my third bin, I have 1, 1, 1 there. So my edge needs to have 1, 1, 1 in the third bin. Then I notice that 0, 1, 1 is an even parity vector, and 1, 1, 1 is an odd parity vector. So that means that in my Cartesian product set, I need the even parity vectors in the first bin, the odd parity vectors in the third bin. And then if I stop and stare at this long enough, it might remind me of something we've seen before. I have 0, something unspecified, and I have 1, and then something unspecified. And if we jump back to what we saw before, we've seen that before. We've seen 0 unspecified, 1 unspecified in our 2-dimensional subcubes of Q4. And we also knew that PS42, our pairing strategy, had an edge that blocked that subcube, specifically 0V10 blocks that subcube. So this is precisely the Cartesian product set that I'm going to use, 0V10. So let's go back to where we were. Remember 0V10. And that's the Cartesian product set that we'll use. So we'll look for an edge inside of this Cartesian product set to block this 5-dimensional subcube. Well, in the last bin, in the fourth bin, these are all stars, so there's nothing to match. So I can pick any even parity vector there. I'll just use the all 0s. And in this second bin here, notice this is a length 3 vector with 2 stars. Well, that's exactly a 2-dimensional subcube of Q3. And this is where my V bin is, my pairing strategy PS32. So I'm guaranteed that there will be an edge from PS32 to block this 2-dimensional subcube. In other words, to have a 0 in its second coordinate. And we could jump back and look at PS32 and look for what that edge is. It's this one right here, V00, has a 0 in its second coordinate. So that's what I want to pick for my second bin. So right here, my second bin from my pairing strategy PS32, I'll pick V00. And now we notice that this edge right here is in the Cartesian product set, and it does match this subcube on the 7 coordinates fixed by that subcube, so it blocks that subcube. And then it's sort of interesting to see, well, because these were stars, I didn't have to pick all zeros here. There were actually, I could have chosen any of the even parity vectors. I could have chosen 0, 1, 1, or 1, 0, 1, or 1, 1, 0. So we actually end up with 4 different edges from this Cartesian product set that block this 5-dimensional subcube. The next thing that we should do is we should check, does our pairing strategy, the union of these Cartesian product sets, does it form a matching? And that breaks into 2 cases. One case would be you select 2 distinct edges from the same Cartesian product set. So we'll look at that through an example. Say this is one of my edges, and say my other edge, I know that it had, say my other edge does a different choice, maybe in the second bin where we're using odd parity vectors. Well, what we need to check in these length 12 edges, we need to check, is there a coordinate, one of the 12 coordinates where one of the edges has a 0 and the other has a 1? Well, if I do a different choice in this bin that uses odd parity vectors, then in this bin, I have 2 different length 3 bit strings. So I'm guaranteed on these 3 coordinates, there will be at least one coordinate where one of them has a 0 and one of them has a 1. And you could say there'll be at least 2 coordinates where they differ because they're both odd parity vectors, but all we need is that there's at least one coordinate where they're different. If we do that in a bin that uses even parity vectors, it's the same story, right? We will be selecting 2 different bit strings of length 3. So we'll be guaranteed there'll be a coordinate where one of them has a 0 and the other has a 1. But when we get, if all we knew was that the 2 edges that we selected, they were different because we did 2 different choices in the bin that uses PS32, we don't immediately know, oh, well, there'll be a coordinate where one of them has a 0, the other has a 1. You know, maybe we might think, well, maybe there's a coordinate where one of them has a 1 and the other has a V, and maybe the other has a 0 and the other has a V. Are we always guaranteed to get this case right here where one of them has a 0 and the other has a 1? And I really like the answer to this, and it's because PS32 is itself a matching. And what we are doing by selecting 2 different choices in this bin, we are selecting 2 different edges from PS32, which is a matching. And therefore, because PS32 is a matching, we're guaranteed on these 3 coordinates, there will be a coordinate where one of them has a 0 and the other has a 1, because these 3 edges right here form a matching themselves. And if you pick 2 different edges from this little set of 3, there will be a coordinate where one of them has a 0 and the other has a 1. So I really like the way that PS12.5 sort of inherits that matching property or exploits the matching property of PS32. If we pick, the other case was we pick an edge from one Cartesian product set and then an edge from a different Cartesian product set, are we still guaranteed that in those edges of length 12, we'll be able to find a coordinate where one of them has a 0, the other has a 1? And this is really nice too, because this uses the fact that PS42 is a matching. So remember, this Cartesian product set got its form directly from the edge V000 in PS42. The other Cartesian product set got its form straight from 1V01, right? 1 cross V cross 0 cross 1. Well, PS42 forms a matching. So if I take 2 edges in PS42, I'm guaranteed to find one of the 4 coordinates where one of them has a 0 and the other has a 1, in this case, the 4th coordinate. We lift that back to the Cartesian product sets. That means there's a bin where one of the Cartesian product sets uses only even parity vectors. The other Cartesian product set uses only odd parity vectors. And so no matter what we choose from this bin and no matter what we choose from that bin, since the even parity vectors and odd parity vectors are disjoint, we're guaranteed that we have 2 different bit strings in that 4th bin. And so there will be a coordinate where one of them has a 0 and the other has a 1. So really nicely, again, the PS12.5 uses, sort of exploits the fact in this case that PS42 was a matching to get that PS12.5 was a matching.
So Eric, you're illustrating this multiplication before procedure, right? In general, so it generalizes.
Yes, it does. It does generalize. And I think I am understanding what you're saying. And this next slide here was sort of to go into more detail, because I just showed one example. of how you would block a 5-dimensional subcube. In this case, for the 12-5 game, we came up with 4 different categories of these 5-dimensional subcubes, right? Each 5-dimensional subcube is a length 12 vector with 5 stars. And we broke the 12 coordinates into the 4 bins of size 3. And we said, well, you could have a bin where you put 3 stars in it, a bin with 2 stars like this one right here, and then 2 bins with no stars. Or there could be a case where you have a bin with 3 stars like this one, 2 bins with 1 star like this one, and then a bin with 0 stars like that one. Or you could have 2 bins with 2 stars, a bin with 1 star, and a bin with 0 stars. Or you could have a bin with 2 stars like this one, and then 3 bins with 1 star each. And those were the 4 categories that we end up with. And they each have their own little unique way of how we would argue that this pairing strategy would block all of them. But we'll see if there's any extra time at the end. We could go back and go through that. But let's just skip that for now. And just kind of recap everything. Our pairing strategy for PS 12-5, it was these 8 Cartesian product sets, the union of these 8 Cartesian product sets. They got their forms directly from the 8 edges of PS 4-2. And then the little sets that we were using to create the Cartesian product sets, the bold zeros were the even parity vectors of length 3, the bold ones, the odd parity vectors of length 3, and then the bold V's were our pairing strategy PS 3-2. And then I think this is what you're saying, Dorn. We can just take this PS 12-5, put it right here, make the bins of size 12 instead of size 3, and we get a pairing strategy for the 48-17 game. Yeah. And then just recursively do that now that we have this pairing strategy, just use those for the V's, do bins instead of size 12, do bins of size 48, get a pairing strategy for the 192-65 game, and just keep going.
It's like a recursive algorithm.
Yes, yes. And that's it. I'd like to thank Ramin, Naimi, Klay, Kruczek, and Thomas Lindia. I'd like to thank Doran for giving me this opportunity to speak to all of you about this. I hope you enjoyed it, and I'd like to thank all of you for listening today. And here are my references.
This ends the formal part of the talk, but we have 2 minutes for questions. Are there any questions? Please unmute yourself if you. I have a quick question. Yes. You reference Beck's book. So yes. This is not covered in his book. These questions were raised in the book.
This specific game of like the Boolean Hypercube and the subcubes for winning sets, they're not in his book. Like I didn't find it in there. I hope it's not in there because I was pretty sure that I had just kind of come up with the idea of like, honestly, I had this thing sitting on my shelf and I looked up at it and I'm like, wait, that would be a fun game to play. Have the little subcubes be the winning sets. And
in hindsight, it's very natural, the unit cube.
Yeah, and so it was surprising to see that I didn't find that it had been done before. So, and it was a lot of fun, a lot funner than I expected. And it was kind of funny because when I first thought about this game, I actually played it with my colleague for a while just to get a feel for it. We're doing the 4-2 game, and we went back and forth. We weren't like thinking too hard theoretically about it, but we went back and forth. We're like, oh, Maker has a winning strategy, and then like we're like, okay, let's write it down, and they're like, nah, Breaker has a winning strategy. And we went back and forth, and I should have tried harder because when Klay and I submitted our paper, the referee was like, I think there could be a pairing strategy for that game because we didn't include that result. And I was like, really? And then I thought about it harder. I'm like, oh my God, the referee is correct. And I kind of wish it wasn't like the anonymous referee thing, because I'd love to give this referee credit for that, because that's the entire direction that I took on this was pairing strategies. It ended up being so fun, and I really owe it to the the referee for that.
That's nice. The
comment.
referee for once was helpful. That's nice.
Yeah. Yeah.
Are there any other questions? Well, thanks so much for coming, and thanks for a great talk, but
Oh,
tic-tac-toe in many, many dimensions. Okay,
Okay.
this ends this talk.
Okay.
Robert, please
Thank
say goodbye. Bye-bye. Thank you.
Okay.
Thank
Thank
you.
Bye,
you.
everyone. See you back here next week.
Thank you.